10.1 correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other. And a linear correlation exists between two variables when there's a correlation and the plotted points are approximated by a straight line. Okay, linear line, that should make sense. So we've got 4 examples, and it might be hard to see those numbers down there, but this one is a positive 0.859, and this one is a negative 0.971, and 0.074, and 0.330. When we're talking about the strength of the linear correlation, okay, linear correlation coefficient is R. We're talking about how good of a line we could draw through. All right, we want to find an equation of a line that really, really represents those points really well. And I kind of look at it as percentages. This one is about 86% good. And this one is about 97% good. So 97% is better than 86%. That's a better representation. But if you look at the points, it's obviously better because those points are so compact. They're tightly packed around what we would expect to be a good line through. This one, it's a little bit less tightly packed, I suppose. The positive number is talking about slope. Positive just tells me that it's going uphill. Negative is talking about it's going downhill. Now, when I get to this one, if you think about percentages, that's like a 7% good to me. That's how I look at it. And you can't even tell when you look at those dots, you can't tell if this is going uphill, downhill, or what. It's just not a very good correlation between X and Y. Then if you look at the fourth one definitely has a pattern. There's some kind of relationship, but it's not a line. That looks like a parabola, and that's not really what we're dealing with here. We're talking about linear, and so this is no good. This one is a non-linear relationship, and that's not really what we want. When we have to calculate R by hand specifically, we're going to need to know certain things like this. And recall that sigma means the sum. So we're adding up all of the x's, we're adding up all of the x squareds, we're adding up all of the x's and then squaring them. Notice the difference between these two. This says find x squared and then add up all of them. This one says find x, find the sum of all of them, and then square it. So the order is kind of important there. This says find the sum of all of the x times y's. We'll see that here in a bit when we do an example. R is the linear correlation coefficient for sample data. Looks like a P, but we pronounce it rho. It's a Greek letter. This is the linear correlation coefficient for a population of paired data. Honestly, the sample is going to be more important. We're going to deal with that a lot more, so we more care about the sample, I think. When we calculate, we must check some requirements. All right, we must check some requirements to see that it's even possible to do what we're trying to do. So requirement number 1, we want to look for a simple random sample. Check to see if those numbers are a simple random sample. Number 2, we are going to graph the points and look and just kind of check and make sure it looks pretty much like a straight line. And number 3, we want to remove outliers. Outliers are going to be a problem because it could really, really change our numbers. One outlier really, really changes the value. Now, these two equations are what we're going to use to calculate this R value. Oh, I skipped something. When we calculate Oh, you know what? No, it's down here. Never mind. The first one looks really, really complicated, but honestly, it's easier to use this one. I would rather use the first one than the second one. It's honestly, it's easier. Okay, the bottom one looks like it's going to be easy, but we're going to have to do something with z-scores. And recall from last chapter when we found a z-score for like an x number, let's say, we took our x number minus the mean, and then we divided that by the sample or the standard deviation of those x numbers. And so that's easier said than done, but that reminds me of stuff that we did last chapter. When we find the r, we want to round it to 3 decimal places. Calculating and interpreting the linear correlation coefficient. We can find this p-value, and the p-value is pretty easy to find using our technology. But alpha represents the significance level. A lot of the times that will be 0.05. Sometimes it will be 0.01. The example that we see here in a bit, we're using a significance level of 0.05. But we're checking the p-value and making sure it's less than or equal this alpha value. If it's greater than the alpha value, it's something else. If it's less than, it supports the claim of a linear correlation. So notice the gray language. It doesn't come right out and say, yes, there definitely is. It says, okay, it looks like there is. And greater than alpha does not support the claim of a linear correlation. The table is a little bit harder to use, but it's going to give us something called critical values. And we can do a similar calculation there by comparing our R number to our critical values. So correlation, if that value, that absolute value of R is greater than or equal to the critical value, and no correlation if the absolute value of R is less than the critical value. It's actually easiest if you look at a picture of this on a number line. Okay. The very next thing, this property down here says that the R value is always between -1 and 1. So if you think about that on a number line, our R value is going to have to be in between -1 and 1. And in between there, you're going to find some critical values. So here's 0, and critical values are always going to be like plus or minus. So at some point, I think we're going to get a critical value of about 0.413 or something. And so you could look at this graph and say, here are my 2 critical values. And you're going to have an R value of, let's say, 0.8. Okay. If we have an R value of 0.8, an R value is right here, 0.8. Basically, what this is saying is if your absolute value of your R value is greater than the critical, so that's putting us right here and right here. You can think of it as distance. If the distance from 0 is big, then we can conclude there is sufficient evidence to support the claim of linear correlation. But what's going to happen if it's less than, if this distance is less than the critical value, R would be inside here. If R is inside here, we can conclude there's not sufficient evidence to support the claim of linear correlation. I think it's a lot easier once you look at that picture. Anyway, R is always going to be between -1 and 1. If you convert to a different scale, R does not change. Value of R is not affected by choice of X or Y. R measures the strength of the linear relationship. Linear, line. It's not designed to measure the strength of anything else. R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value. All right, now Number one, we want to find the R value using technology. And this is going to be kind of easy. Down here at the bottom, I've given you two different methods. I've got directions for using StatDisk and directions for using TI. So you can follow those. I would recommend StatDisk. That's what I'm about to show right here. So we go to statdisk.com and we want to enter the data points. So 5, 6, 4, 4, 5, and 6, 9, 3, 2, 11. Okay. So what we want to do here is we want to select the analysis drop down, and we want correlation and regression. And then we have to select these columns. Select column 1 for the X, select column 2 for the Y, and evaluate. And it gives us all this stuff, okay? We can click over here and look at a plot. There's only 5 points. Looks like it kind of makes a straight line. It's hard to tell with only 5 points, but we really want these results. And specifically what we're looking for is the correlation coefficient R. All right, so right here, remember earlier it said round to 3 decimals, so we're going to take 0.795. 0.795 right here, 0.795. It'd be the same thing, of course, if you do it with a TI. So feel free to follow those instructions on your TI and find the same thing. You'd have to find that correlation coefficient R. Now, let me back up a second. I didn't really tell you what this problem was about. You've got data marked chocolate and Nobel. What we're trying to do in this example is we're trying to see if the variable chocolate consumption correlates at all to Nobel Prize winners. All right, and so use your intuition and think about if that makes if those two things should be related. The amount of chocolate you consume is related to whether or not you win a Nobel Prize, or how many people would win a Nobel Prize. Sure doesn't seem like those two things should be related. Okay, and so that's kind of what we're trying to figure out here with this correlation coefficient. This number is a number for how well those two things are related. Now, we don't really know if this really tells us there's a relationship or not. We're kind of trusting our intuition here and saying we don't think so. But that's like a 79% match for the numbers. So 79% is not terrible, but it's not really enough to answer the question if we think those two things are related. Okay. Now, example 2 is showing you how to find the R value by hand. Now, you're going to think that's kind of pointless because we just found the R value. It's going to be 0.795. I already know the answer. But here's how you would do it by hand. So, X numbers. And then sigma X is just sum up those numbers. Add up those numbers, you get 24. The Y numbers. 6, 9, 3, 2, 11. And sigma Y, add them up, we get 31. X squared, literally just square all your X numbers. 5 squared, 6 squared, 4 squared, 4 squared, 5 squared. Sum is 118. Y squared numbers. 6 squared, 9 squared, 3 squared, 2 squared, 11 squared, and their sum is 251. I know I'm kind of doing this quickly. I don't want to spend all day with the numbers. X, Y, you're multiplying your X number times your Y number. So 5 times 6 is 30. 6 times 9 is 54. 4 times 3 is 12. 4 times 2 is 8. 5 times 11 is 55. And then find the sum, that's 159. We fill out all those numbers in that chart because we have to fill in all of the arguments in this equation. All right. So n isn't in my chart, but n is just how many numbers there are. There's 1, 2, 3, 4, 5. There's 5. N is 5. Okay. So we're going to have, all right, big fraction. N is 5. And then in parentheses, we've got the sigma of the xy. Sigma xy is 159 minus sigma x is 24. Sigma y was 31. And then on the bottom, we've got a square root of n is 5. And sigma x squared is 118 minus, notice the difference. This is the sum of x squared. That's going to be 24 squared. Notice the difference. One of them is sigma x squared. The other one is sigma x squared. Sounds the same, but it is totally not. Times another big square root. N is 5. Sigma y squared is 251 minus sigma y squared is 31 squared. So we plug all those numbers in, all right? And we type all that stuff into the calculator. You can clean it up if you want. The top's going to be 51, and the bottom's going to be square root of 14 times the square root of 294. But you can clean that up even more and find that the answer is 0.795. Well, yeah, we already knew that, right? We already knew that because of the technology. Now, example 3 wants to do it again, but this time using that other formula. We already know the answer. What's the answer? 0.795. I already know that. But we're going to do it again. So your x numbers, 5, 6, 4, 4, 5. Your y numbers, 6, 9, 3, 2, 11. Okay. Now, in order to calculate the zx numbers, you have to remember that zx is going to be x minus your mean over your standard deviation of your x. Okay. So you're going to need to find the mean and the standard deviation of some of those numbers. So check it out. The mean is 4.8. The standard deviation is that, okay? So, you'll have to use your calculator or something. A spreadsheet will do it. I wouldn't want to do it by hand, but you can find the mean and the standard deviation of those x numbers, 4.8 and 0.83666. And so what you want to do is go through and use that calculation for each of these numbers. Got to do it for the first x number. So it's going to be 5 minus, what was it, 4.8? 4.8 over 0.83666. And if you do that calculation, you get the first zx value of 0.239046. Okay. It's kind of a pain because you're going to have to do it for each of these numbers. So next we would do it for this number 6. And it's going to be 6 minus 4.8 over 0.83666 right there. Do that calculation, I get 1.434274. round it off to 6 decimals, whatever. Keep going. Do the next one. You're going to get negative 0.956183. Of course, the next one is exactly the same. And then 5, we've already done a 5. We got 0.239046. Now I have to do the same exact thing for the y numbers, all right? So I would need to find another mean and standard deviation, this time for the y numbers. Mean and standard deviation. .2 and 3.834. So your z number for your y is going to be y minus the mean over the standard deviation of the y's. The first number is going to be 6. This is your 6, right? This is your first y, number 6, minus the mean was 6.2 over 3.83406 or so, rounded. And that first z number for my y is negative 0.052164. So you do that same calculation for all of the y numbers. The next one is 9. You plug it in, you're going to get 0.730297. Next one, negative 0.834625. The next one, negative 1.095445. And the next one, 1.251937. So I found all those zx's and I found all those zy's. I think that's more complicated than what we did on the last example. But anyway, I found those. And then in that last column, I need to multiply the zx times the zy's. So this times this, right? And we're going to get negative 0.012470. And the next one, 1.047446. And then 0.798054. 1.047446. Strange to me that I got a duplicate number. That seems pretty hard to believe. 2.299270. Right, so I found all those products, and I need to do the sigma, so I add those numbers up, and I get 3.179746. Whew, it's a lot of work. That's a lot of work that I don't want to do. So then I can go look at my R formula. The sigma of those products was 3.179746. And then on the bottom, I've got n minus 1. I remember n was 5 because I had 5 dots. So 5 minus 1. I'm taking 3.179746 divided by 4. And guess what I get? 0.795. Okay, but we already knew that, right? I would never want to calculate this way. Okay, I wouldn't want to do it. If I'm going to calculate, I'm going to do it the other way, or maybe use technology. Either way. Okay, so that is the correlation coefficient. We still haven't answered the question of, is there a linear correlation? We found the coefficient, but we don't know if those two things are correlated. And that's what we're trying to answer in this section. Now, they take the same problem, the chocolate and the Nobel Prize winners, And this time they give me 23 pairs of data, not just 5 points, but they give me 23 points. And so if you were doing this on your TI, you would need to enter in those 23 data points. Okay. It says using the value for R equal 0.801 for these 23 pairs of data and using a significance level, remember that was alpha, of 0.05, is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and numbers of Nobel winners? The first thing you need to do is check the requirements. And so if you go back, there were 3 requirements. Requirement number 1, is this a simple random sample? And we're looking at Nobel Prize winners. It doesn't really seem to be a simple random sample. Doesn't really seem to be a simple random sample. And so really, it's kind of silly because that's going to throw our numbers off. And we don't know that we can really make an assumption here. But anyway, let's get past that. We'll come back to that later. Requirement number 2 is look at the scatter plot. It's supposed to make a line. So check it out. I'm going to go to StatDisk and I'm going to pull these 23 numbers in. Okay, and that's what I like about StatDisk is it's got a lot of our examples already in it. So if I go here, I'm going to go back to home. Here's my 5 points. I want to clear them out. I'm going to go to data sets, and we are in the 13th edition. And I can go down here and find Nobel laureates and chocolate. And that pulls in a whole lot of information. If you scroll down, it's got 23 data points. That's what we needed. This is our information. All right. I want to do an analysis, specifically correlation. And what we would want to do is set the first column to be chocolate, second column Nobel, and evaluate. Okay, so I've got this stuff and I can see a correlation coefficient here, and what they say it was 0.801. Okay, yeah, that's good. But what I want up here is the plot. Remember, when we look at the scatter plot, we want it to pretty much look like a straight line. Okay, and yeah, okay, all right, I could see that. It looks pretty much like a straight line, so that's all I really cared about there. Look at the scatter plot. Does it kind of look like a straight line? Okay, sure. Straight-ish line. Yeah, probably good enough. Then requirement number 3 was look for outliers. I don't see any. So I think we're pretty good there. All right. Simple random sample doesn't seem to be a simple random sample. That might be a problem. We'll just have to see about that in a little bit. All right. So 4B. Find the p-value from StatDisk or your TI and give the implication. So when we were at StatDisk, specifically the results, you can see right there in the middle of the screen, the p-value is 0.0000. The p-value is 0.00 right there, 0.0000. Okay, and you don't really know what that means without looking at alpha. Okay, alpha, if you recall, a couple of slides back, was talking about the significance level, and that was over here in this box over here. The significance level was 0.05. That's alpha. That's alpha for this problem. So alpha is 0.05. So we had something earlier that said if the p-value was less than or equal to alpha, which it is, the implication is this supports the claim of a linear correlation. Notice the gray language. It doesn't say that there is a linear correlation. It just says that there could be. This supports the claim of a linear correlation. All right. So it says use table A6. We're kind of torn between two worlds. The old world is we had to use a bunch of tables and charts and stuff. The new world is everything's done through technology and calculators and websites. And so this has taken us back to the old world, how we would have to do this without the technology. We've got this table to estimate the critical values. Okay. So the critical values, well, it's hard to find, but you got to remember that n was 23 in this example. So if n is 23, we're looking in between 20 and 25, right? And for a significance level of 0.05, that means we're looking right in here somewhere for our critical values, in between those two numbers. And so I'm going to estimate, okay, I'm going to estimate that your critical values is about, I don't know, between those two, let's say it's about 0.42-ish. Okay, I can't really get very close, but I can estimate in between there. It's closer to 25 than 20, so it's got to be closer to 396 than 44. I'm guessing it's about that. Now, keep in mind, it's always going to be plus or minus, so plus or minus 0.42. That's kind of our estimate. All right, that doesn't mean anything to us yet. This says go to StatDisk to find the critical values. And so back at StatDisk, we noticed the critical value was right here, 0.413. That's pretty close to our estimate of 0.42. 0.413 plus or minus. Okay, great. So plus or minus 0.413. That's better. So what does that mean? It takes us back to that number line. Remember how I said earlier that R had to be between -1 and 1? Okay. So here's a number line, and our critical values are right here at positive 0.413 and right here at negative 0.413. Does anybody remember the R value that they gave us earlier? Well, I guess we could look at StatDisk. Yeah, the correlation coefficient was about 0.8, right? 0.801, 0.801. So think about where that is. 0.8 R equals 0.801. All right. The language of it said, where was it? The absolute value of R was greater than or equal to the critical value. It said we can conclude there is sufficient evidence to support the claim of linear correlation. So the implication, there is enough evidence to support the claim of a linear correlation. So is there or isn't there? There could be. There's enough evidence to support the claim of a linear correlation, but they stop short of telling us that there definitely is. So do these results make sense? Go back to the very start when I introduced the chocolate and the Nobel Prize winners. Okay, your intuition told you that that doesn't seem like those are related. Okay, so do these results make sense? Not really. It seems absurd that chocolate and Nobel Prize winners are correlated. But then you go back and remember that first requirement check, okay? Remember that first requirement check that said, is this from a simple random sample? And it wasn't from a simple random sample. What that tells me right there, when that didn't check out, that tells me that my numbers could be off slightly, or I'm not maybe going to have the same exact outcome as what it appears. So according to the numbers, there's enough evidence to support that claim, but it doesn't really seem that way in real life. The value of r squared, sometimes we'll see r squared instead of r, but the value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. You might want to read that again. The proportion of the variation in y that is explained by the linear relationship between x and y. So we've got example 5. Using the 23 pairs of chocolate / Nobel data, we get R equals 0.801. What proportion of the variation in numbers of Nobel laureates can be explained by the variation in the consumption of chocolate? Well, that's just R squared. So if R equals 0.801, then what's R squared? .642. Or about 64%. Okay. About 64% can be explained in the variation. So 64% can be explained in the variation. Or, in other words, 36 cannot be explained. By the variation. Okay. So what does that mean? It means something that you've probably heard before. Correlation does not imply causality. All right. Just because they're correlated doesn't mean that one causes the other. All right. Just because somebody eating chocolate doesn't mean they're more likely to win the Nobel Prize. They're correlated, but that doesn't mean that one causes the other. Common errors. Number 1, assuming that correlation implies causality. That happens all the time. There's something called lurking variables. So beware of lurking variables. Something else that affects it that's behind the scenes that you didn't think about. Lurking variables. Number 2, using data based on averages. Averages tend to suppress individual variation and inflate the correlation coefficient. Makes the correlation coefficient higher than it should be. And then number 3, ignoring the possibility of a nonlinear relationship. Okay. Could be something else. It could be a parabola shape, a quadratic relationship, or something like that. All right. Now, this is the end of part 1 of the notes. Formal hypothesis test is going to be part 2. I think this is a good place to stop right there at the end of part 1.